Well, on the bench we have our next project, and this one's going to be a pretty interesting one. This is a Soundcraftsmen PM860, and these were very interesting amplifiers in their day. They were from, I think, from the 1980s, and believe it or not, this little tiny amp, you can see it's not that big, is rated at 205 watts per channel. And they're very interesting the way they're designed. The power supply is really not anything you've ever seen before. The outputs are MOSFETs, and they're designed to handle very low impedances and difficult speaker loads. Very interesting amplifier. Also, to me, I've only worked on one of these before, probably one of the more or most difficult amplifiers I've serviced, just because of the way it's put together. So I'm not gonna, I know this one works, but it doesn't work really well. It clips easily. The components are really old and dried out, and when you see inside of this, you'll see why I'm kind of reluctant to even turn it on and test it until I take it apart and check things out. So if that sounds interesting to you, stay with me and see if we can learn some things about this. Alright, I have the cover off, and I have the amp kind of turned sideways here so you can see the whole insides. And as you can see, this is not really the easiest little amp in the world to work on. Over here is kind of like your driver preamp power supply. Well, no, it's really not. This is your power supply section here. And these four screws here that are all rusted go into the top of the main filter capacitors, and if you look at them, they're these great big can capacitors, and they're most likely dried out. That's one of the problems that this amp has when I tested it, was that it kind of bottoms out pretty easily, which is a good sign that those caps are probably starting to go bad. Yeah, this thing has 6 MOSFETs on each channel, so you can imagine the amount of power this thing can deliver. It has a fan, and it's using a synchronous, kind of one of those motors like you would see in a record player. Okay, it's not a synchronous motor. It's, I forget the name of it. I'm having a senior moment. But bottom line is, it's a pretty quiet fan. You hardly hear it. There's a lot of little electrolytic capacitors, a lot of old semiconductors in here, but they're probably all going to be good. These are really bulletproof MOSFETs here. You know, the resistors are good. I mean, really, recap, and you know, some of these wires, some of the wiring here kind of leaves something to be desired. Granted, there's not a real high gain in this amplifier because it's just a power amplifier, but things like over here, when you look at the input, it originally had 1/4 inch inputs, which I removed, and at some point in time there was this was put in these little RCAs. So we're going to upgrade these to a little better quality, maybe go to some shielded wire to make it a little quieter, and then we're going to completely disassemble this amp, which really needs to be done if you want to properly restore this and clean it. We're going to look at the capacitors. I do have some replacements, but I doubt that they're going to fit. They're just a little bit, well, no, they're about the same height. So we'll see how that goes. The lead spacing's a little wider. We'll see how, if we can fit these in. As you can see, there's 11,000 microfarad in there right now. These ones are 24,000. I don't know. I'll see what else I have. I may have some other ones that are more suitable, but definitely those are going to need to go. These are, like I said, this is an old amp. It's been around for a while. You can see it's got some rust on the transformer, but big hefty transformer. This is really pure classic analog. There's no digital in these. So I'm going to start with the power supply. And also, I have some service manuals from some Soundcraftsmen gear, but this is not exactly the one I have. I have a very similar one for the PCR. Let's see. I guess this is the right one. Nope, this is the PCR 800, and the one I have is this is a PM 860, but they're very similar. But I'm going to see if I can get the exact schematic for it, and then we'll go from there. But a lot of work cut out for us on this one. Just cleaning, if nothing else. So, all right, let's get some documentation and then make a game plan. Okay, so I've had to have this thing torn down a little bit further, and I took the capacitors, the main filters here. They're 11,000 at 75 volts, and that's pretty scary. 11,000 microfarads for an amplifier that in total between both channels is supposed to produce 410 watts total, free, you know, at 8 ohms, you know, 205 watts per channel. That's an awful lot, you're asking. Now this thing does have a very huge power transformer, so it can deliver an awful lot of current. But the other thing is these are rated at 75 volts, and you're imposing 70 volts. You know, it's a 70 volt power supply DC rail, plus and minus. So you're talking an awful lot of, you're asking a lot out of these two little capacitors. I tested them. I even put them on a little bit of a stress test, and they're perfect. They work fine, and they'll probably work, you know, they're sealed. There's no signs of any leakage. They're in very good condition. So, you know, part of me thinks that I think this would be just fine to leave it as it is. And then, you know, part of me also says, well, they are a little bit underrated. And this amp does show, when you, anytime I've used these amps, they work fantastic at normal listening level. But anytime there's a very large bass passage or something that's, you know, where you're drawing instantaneous current, you can well exceed that 205 watts easily for a split second. And that's where the reserve of the capacitors come into play. So really you should probably have, I mean, you look at the Pioneer SX1050 projects that we did in the past on the videos. Those are 20,000 microfarad capacitors for only 125 watt per channel amplifier. So it kind of gives you an idea. Now, of course, well, they even have a big toroidal transformer, so can't even use the transformer as an excuse. So what I've done is I have found a drop-in replacement for these. It brings it up to about 15,000 at 100 volts, which is a lot safer margin, in my opinion. With line voltages creeping up and up here in the United States, you know, it can affect all that. So that's one option. The other option is I have these in stock, and believe it or not, they're exactly the same spacing. Everything is good there, but we have a little bit of problem here with height. So I can either modify the case and use these, which are 33,000 microfarads, or I can use the drop-in replacements for these that are 15,000. Not sure yet what I'm going to do. I'm going to think on that for a little bit. Now, for those of you, you know, I get a lot of comments on my videos over, you know, even over time, and I get people who say they really appreciate when I get into the theory and when I talk about the, you know, the design and how the functionality of these. I have other people that say, shut up and get on with it. I just want to see you solder parts in and test it and how it works. You know, your videos are too long. Well, here's my take on this. I try to play these videos for everybody to appreciate. It's also my hobby. I enjoy doing it. And my thing is, if I go ahead and I talk some theory and some things like that, for those of you who enjoy that, you can watch it and learn, or just, maybe add your thoughts to it, whatever, which is great. For those of you who don't like that, there's a fast forward button. You could skip through it. And I have plenty of other videos on there as well that you can watch. You don't have to watch the ones that are too long for you. So in my opinion, if I feel like talking, I'm going to talk. And you know where the skip button is, use it. That's my opinion to all of you. And if you appreciate it, that's great too. I'm glad I can help you and share with you. I know a lot of other people who've made long videos in the past have really helped me learn things that I didn't know. That's how I learn. So anyhow, that's enough of my soapbox for that. I don't mean to offend anybody or anything like that. I wish you all out there the best, and I appreciate all the good comments. So that being said, I'm going to go a little bit over how this thing works. They've split this thing basically into two different sections. This section up here is your power supply, and it's pretty unique on this compared to what we've seen in some of the past videos. This is a pretty common circuit, with little variants of it on some of the larger, when you start getting up to the 500 watt per channel and things like that, you start seeing things like what you're going to see on this one. And over here, you have MOSFETs instead of transistors, but they're P channel and N channel, just like you have PNP and NPN, so it's still a complementary circuit. This main board down here is your, all of your driver and output section all in one. So this is the whole stereo amplifier right here. This is the power supply right here. Here's your transformer. You have your cooling fan, and that's pretty much the whole system. I'm going to go over some of the schematics with you guys and explain some of the things, how it works. Again, if you don't like it, hit the skip button. If you do like it, I'm glad I can be of some help. So let's clear the deck here a little bit. I do have some parts on order, and when they come in, I'm going to get some things replaced, and we'll go from there, and we'll explain some things, why I'm changing some things as we go along. So if that sounds good to you, stay tuned. We'll be right back. Alright, we're going to start off with the power supply. So this whole page is the power supply module. And it is kind of unique compared to a lot of the traditional receivers and amplifiers you'll see out there. But I'm not saying that this is the only one of its kind out there, because there are other ones that have similar designs to this. It's just something new to this channel that we're going to look at. So first thing you notice on here is the main power supply for the DC rail for your plus and minus differential voltage for the outputs. You don't see a standard bridge rectifier. Okay, so we're going to start with that, how it all works. If you look down here, this teeny tiny little section of the whole schematic is actually the gigantic power transformer that I showed you inside the amp. And with these windings, you have your primary windings and your secondary windings here. And basically what you've got is you've got a high current winding and a low current winding on your secondary. Now the low current winding goes up to here, and it's the little green and red wire, and those feed into a little bridge rectifier, which turns into your plus and minus 15 volts. Okay, so this is your, I call this your signal voltage. This is your plus and minus 15, and it's going to drive all of the logic and all the different parts of the circuit that require reference voltages and logic voltages and so forth. They're both regulated by some linear voltage regulators, and if you look these up, they're LM320 and LM342 or whatever. They're pretty much a 7815 and a 7915 for the most part, is all that is. Now, if you notice, there have been some things added to this schematic, drawn in, because these are later revisions in the, I believe, in the PM860. I haven't really studied this closely enough to see if it's on the one that I have or not. But we'll go over it and explain why it's in here. First of all, they call this, to see why this all has to be here, let's start at the very beginning here. So I went over the plus and minus 15. If you notice down here, you've got 4 SCRs. These devices are SCRs, silicon controlled rectifiers. What they are, anybody who doesn't know what an SCR is, I know a lot of you electronics folks out there know what it is. For those of you who don't, this is just a diode that you can turn on. Okay? In other words, if I apply a voltage potential on this diode, it will not conduct in either direction. Okay, now we know that a standard diode will conduct in one direction when you forward bias it, but when you reverse bias it, it does not conduct. Okay, and an SCR is just the same. It's a diode, but it's a special diode that in the junction you have to apply a small trigger voltage, and this is called the gate. This element is called the gate. You have to apply a small gate voltage in order to get the electrons to start flowing through the diode. So it'll sit there and block until you trigger it. Once it triggers, as long as current continues to flow through that SCR, okay, the SCR will stay gated. In other words, it just will act like a normal diode. Okay, as soon as the voltage drops below the threshold, which is, you know, usually a volt or two, couple volts, the diode will turn off, or it will extinguish. Okay, and it'll go back to that state where it is non-conductive in either direction unless there is a trigger voltage present on the gate. So you only need the gate to start the conduction. Once it's conducting, it'll continue conducting until you stop the flow of current through the diode. Now, why would you want that? Okay, so we have to go through this a little bit step by step. First of all, there's 4 of them, and if you follow the line, you have this phase, or this leg of the transformer winding. So this is just a transformer winding here. So really, if you looked at it, this is just the secondary winding of your transformer here. And the center tap, I believe, is going to ground, kind of like that. In this direction, you can see that you have one diode for the positive going part of your AC waveform, and another diode, okay, for the negative going side of the waveform. See, so when it will always steer it in one direction. This is just a standard bridge rectifier. It's just drawn differently. If you took every other component out of here and just put 4 diodes in here, this would just be a bridge rectifier, and you'd have your positive and negative voltage with respect to ground out here. Okay, so when this one swings positive, it's going to allow the positive go through here, and when this one swings positive, it lets the positive go through here. So either way, it's always going to be positive. In this one, it always passes the negative going portion of the waveform. Okay, in the same manner. I hope I'm being clear enough. Now, why would you put SCRs here? Because think about it. Remember what I said about an SCR. Anytime current stops flowing through this, it turns off. So what that means is every half cycle. So in other words, you have a positive going cycle, then your zero crossing where you go through 0 volts. Okay, so you know, if this is 0 volts here, your AC waveform's doing this, right? It's swinging positive then negative. Okay, and anytime you go through this 0 crossing right here, there's no current flowing through here. So guess what? The SCR turns off. So that means every time you cross the 0 point, you have to turn these back on again, or they will extinguish. Okay, so this type of a circuit with these SCRs bias or set up this way is called self-extinction. In other words, it will always turn itself off every half waveform, okay, every half cycle. So every half cycle this turns off unless this is turned on. Now, the reason we would do this is, let's say we have a problem, we detect a problem with power somewhere, or there's a short, or there's an issue. All we have to do is remove this tiny little trigger voltage to these two gates, and these will no longer turn on. And I can shut this off in 1/120th of a second. So in as little as a half cycle or less, whatever portion of the half cycle, I can cause this to turn off. And as long as I don't put any more signal here, it won't turn back on. So these SCRs act like a bridge rectifier as long as these transistors are telling the gates to stay on. If I tell these transistors to not bias on, and I don't put voltage on the gates, within a half a cycle or less, this whole thing shuts off and everything turns off in the amp. So I think you've already figured out that's actually part of a safety circuit. And that's what all the rest of this whole schematic is all about, okay, or at least most of it. So if you follow back, you have these two little signal transistors that basically their job is to keep the gates going on these SCRs. They are driven in turn by these two transistors that are driven in turn by this little op-amp circuit up here. So the first thing we're doing is, when your 15 volts comes up, all of this turns on. This thing monitors and makes sure everything's ready to go, and then it outputs a voltage that turns on these transistors, that turns on the SCRs. Okay, now this was added up here is basically just a little RC time constant circuit, and all its job is doing is, by the delay of this charging transistor or charging capacitor here through this RC time constant, I'm delaying when I turn my DC inverters on. So basically it's allowing the transformer and some of these a very, very short period of time to come up so that all the surge current doesn't draw so much down on your incoming line and possibly blow a fuse. So this was probably added because they were having intermittent, the main fuse was blowing in the, you know, down here near the power cord. Now, we're also monitoring your plus and minus 70 volts right here. Okay, so you have two more comparator circuits. And what they're doing is, if our 70 volts plus and minus, if either one of the rails drops out, so either the plus 70 volts or the minus 70 volts drops out here or here, it's going to change this whole circuit, and it's going to cause this whole thing to turn off. Okay, and this is a safety circuit basically. Now they didn't just stop there, okay, because not only can the voltage change, but the current can change. And if you look at this top up here, we'll talk about this a little bit more how it works, but this is actually a current sense, and it actually is being picked off of the actual output of your power amplifier here, right here on your main output MOSFETs. So it's just taking a sampling of the current flowing through, because if I measure the voltage drop across this little 0.27 ohm resistor, I can calculate how much current is flowing through here. And if it's excessive current, okay, once again, this whole circuit here can work and come down in this whole thing to tell the machine to either turn off the high, you know, the power to the outputs, and it can also drive this little fan circuit down here, and we'll talk about that in a second. There's also three other safety sensors. There's one for your channel 1, one for channel 2, and these two here are over temperature sensors. So these are attached to the heat sinks, and what they do is they monitor the temperature of the heat sink. So if the amp is running way too hot, okay, after a certain period, it can actually throttle the fan up higher. Okay, so, and we'll talk about how it does that here in a minute. And down here, they also monitor the transformer windings. If the transformer overheats, rather than burning up the coils of the transformer, it can cause the fan to kick on or cause the system to turn off. So that's pretty much, and again, I don't have a theory of operation for this. So this is just after kind of looking over the schematic. I believe that's what's going on here. And if some of you have some corrections for me out there, feel free to share them on the comments, you know, so that everybody can be on the right page with this. But as far as I know, that seems to be what's going on. And again, I think this current sense was also added as extra protection. It wasn't originally there, because you can see it's been drawn in on the schematic, at least after I got it. What else? Okay, the fan. If we look at this fan circuit, it's kind of neat. We use this kind of circuitry in X-ray on certain things too. And basically, this is a bridge circuit. And basically, what's happening here is you have your AC line, and the negative side of one side of your AC line just goes straight through to the one side of your fan. The other side, if you look, goes through a bridge rectifier and to the other side of the fan. Now, if you follow this bridge rectifier, it will pass the AC all the way through here, but it has to go from this end to this end, have to be connected to show like a short to pass all the current through to the fan. So if I open the positive and negative side, there's no current flow through the positive and negative, no current will flow through the fan. Now, if I just took this section right here, where I, you know, not including what my hand is covering, I have a 10 watt 680 ohm resistor. And that big resistor, you guessed it, is going from the positive to negative of the bridge, completing the circuit through here. But this 680 ohm is dissipating some of the voltage and current to the fan. So what it's doing is, as long as this goes this way, the fan is going to turn very slowly, and therefore it's going to be very quiet. So it's going to keep the amplifier from being too noisy with all the air blowing through it. Now, if I sense a high temperature fault, or I'm drawing higher current, but I'm not unsafely doing so, it's just I hit a certain trip point based on this circuit, there's this little circuit here called an opto-isolator, and it's a little integrated circuit chip, and you can see it right here, and there's that big resistor. And what that's doing is that's giving you electrical isolation between your incoming mains voltage and the rest of the circuit. That's all this does. So basically inside here you have a LED, a little infrared LED, and then an SCR that is also triggered by that light. Okay, so it's a photosensitive SCR. It's a special component. And when this thing trips, it'll fire off this SCR. This SCR will then conduct as a short. In other words, it'll, instead of acting like a resistance, it now acts like a short, with the exception of your 0.7 volt drop. This is basically a closed circuit here, and it allows all of the current to bypass this resistor and to flow to the fan, and the fan will then run at full speed. So this is a two-speed fan circuit. It's just a fancy, isolated two-speed fan circuit. So it can run quiet when it's not running hot and not running high current and not running high power amplifier. And then it can also run at high speed to keep the amplifier cool when it's under a heavy load. So that's what this is. So you can see a lot of, for as tiny as this whole amplifier box is, there's a lot of thought and a lot of design consideration that went into this. That's all good stuff, and I really solid circuitry design. I like it. The thing I don't like about these amps is they're very wiry. If you go back up to here, to make that all happen, we have bunches of these wires going everywhere, and a lot of them are connected with these little push pins, these little header pins. Like, this is just a pin out of a Molex connector, and it's just kind of shoved on there, and I guess as long as there's no tarnish and as long as they're tight, you get a good connection. But you know, for a high-end audio amplifier, anytime you have mechanical connections like that, you're kind of asking for trouble down the road. The other thing is, for the incredible amount of current and so forth that this is all going to draw, especially on, you know, in a surge, these little wires that are picking off your voltage and sending it down to the main output section, that's pretty thin wire for, you know, for high current. So one of the things I may consider doing is I may remove these little binding posts, and I may solder good quality Teflon coated, silver tinned wire into here. I don't know yet. I'm thinking about it. And the other thing I may do is the actual power supply wires. I may solder them as well and go with a little higher gauge of wire, just to have a better transfer of the current. Now, for back to the power supply, that is the whole power supply. So that's how it works. So other than having the soft start and having monitoring to be able to switch on and off the power supply, other than that, the power supply is very basic. You have a linear voltage regulator for plus and minus 15, and those are your only two low voltages you have. Then you have a plus and minus 70 that's basically a bridge rectifier and gigantic capacitors, two of them, two big capacitors. That's it. There's no little noise snubbers across there. You know, normally sometimes you'd see the little ones. There's nothing shunting here. There's nothing. It's just a very simple, as basic of a power supply as you can have. So I hope that makes it a little clearer and makes this a little less scary to work on. Okay. Now if we move over to the amplifier, again, you're going to see things that are similar to a normal amplifier and things that are different. In the beginning, at the front end of this amp, it's very traditional. You know, you see this all the time in all the normal audio amplifiers. And you know, you go into your phase inversion, you go into your pre-drivers, your drivers, and then you finally have your main drivers here, and where it starts getting a little, and then your bias is set up through here. So if you look, instead of having adjustable bias right here, you have a Zener diode here, a Zener diode here, and then two regular diodes, and that kind of regulates the voltage here. And I have a feeling that a lot of these transistors are hand-picked matched pairs, because I don't really see. Okay, so there is some adjustment here for idle. So yeah, this actually, it does have an adjustable bias. There it is, bias. So you can adjust that. But these just raise up your voltage to the proper level that it needs to be to get your bias range where it should be, and then you trim it with this circuit here. So it's actually a good bias circuit, and it's solid. This has been around for a long time. Where you get a little different is, instead of using transistors, we're using MOSFETs. And the advantage of MOSFETs is their ability to deliver high amounts of current at very low, across very low impedances. So theoretically, if this is all set up properly and it all works properly, we should see some really impressive output, especially when you deal with the bass, you know, low notes, low frequencies, getting out to the speakers. And these should have a fairly good damping factor too. So this should be a really good performing amp once it's all cleaned up and restored. At the output, you still have your isolation coil here, which is just a 1.2 microhenry coil, and that can be seen right here. You can see one of them. Very simple. And you see the Zobel or Zobel, however you want to pronounce it, network right here. And all of these three components, what they do is they decouple any kind of stray back, what do you call it? Any kind of stray signals from getting back in and causing a short in the transistors here. And that also prevents the amplifier from running into oscillation at high frequencies by kind of snubbing that. This is, even though they call it a Zobel network, it's a type of snubber circuit. Okay, and you can look up snubber circuits online. They talk about it. So it's a basic snubber circuit. So it's a well-designed amplifier, and it should be a really good performer. And you can see your plus and minus 70 going in. You have an N channel and a P channel, you know, MOSFET, just like you would have an N channel and P channel transistor, or NPN, PNP transistors. So it's a differential complementary pair. So really, other than the MOSFETs, it's a nice, solid, tried and true amplifier design. And this thing should work really well because it has, these are way overrated for what this amp's rated at. You know, this is one channel you're looking at. You're not looking at two channels. There's two of these inside there. This is just half. This is, you know, right channel or left channel, whatever you want to call it. But that being said, those SCR, or I mean those MOSFETs there, are literally, those are 125 watt MOSFETs or 150 watt MOSFETs each, and there's 6 of them in there. So these can handle an awful lot of power, and they're rated, I think the P channel ones are good for 200 volts breakdown. These are good for 400 volts breakdown on these ones. So you're talking big time over design, you know, for current. And you know, the voltage is higher than the plus and minus 70, so everything's over designed here. So it's going to be solid, and it's going to be able to deliver a whole lot of current to your speakers. So I'm kind of excited to get this. You know, I've worked on one before. It was a long time ago, like in the late 1980s, and it didn't have any, it wasn't a major problem. But what I will say is these amps really do sound really good. You know, they have a wonderful sound. The only thing I didn't like about them was they can tend to be noisy, and that's because if you look here, you know, here's your input wires. I mean, they're twisted. There's no coax. It's right next to a fan motor. Really kind of a lousy design there. So it's an audiophile design for an amplifier, but the mechanical layout of this particular amplifier leaves much to be desired. So we're going to try to, we can't totally fix everything, but we can maybe make this a little more friendly to use in the home audio environment and get it to be nice and quiet, and also improve that short term. That was the biggest issue with these. If you look here, there's this little red LED. It's just set up so that when the amp goes into clipping, the red light will flicker on as long as you're in clipping. So once you exceed the actual swing of this circuit, this LED lights up to tell you that you're causing the amp to go into clipping. The amp can clip even easier, though, under sustained low frequency because of the limitation of the size of this capacitor. And that's why I'm really considering whether I want to go with a much larger cap. Then we have to make sure that those SCRs here can handle the extra surge current of those capacitors when they're first turning on and charging up initially. So kind of one thing leads to another. I don't know. Again, you know, I'm not doing this for a customer or anything. I'm just restoring it, and it might end up down here on my system as a high-powered amp if it sounds good. I have have a good preamp coming in to pair up with it. So that's kind of why I thought I'd pull it and take a look at it and see what it looks like. This has been sitting in storage, you know, in my storage unit for many, I mean, like almost 30 years it's been sitting. So, and like I said, you know, from the other one I worked on, I knew it was a good amp when I had a chance to pick it up back then, so I grabbed it and never really did much with it. So what you see is how I got it. That's about all I have to say about this now. I'm going to go ahead and get some components changed out in here and get this cleaned mainly. It's just a big mess. And then well, maybe if there's anything interesting with the biasing or anything like that, I'll go ahead and show that part to you. But other than that, once we're done with that, we'll put it together and we'll see how it performs. This is a good one we might want to hook up to the test gear and put it onto the dummy load and really unload everything this thing's got and see what it does, because I have a feeling it's going to be pretty impressive once it's done. Alright, my long speech is done. You guys can unclick your fast forward buttons if you've done so, and we'll be back here after a bit. Here's the finished product, and as you can see, I made a few changes to the amp. Of course, I recapped it. Inside, I did find, like I said, some drop-in replacement capacitors that were a little more suitable for this size of an amp. And you can see them right there, and they're rated at 15,000 microfarads at 100 volts instead of 75, because there is a solid 70 volts in here. So 75 volt capacitors were kind of running up there. They're Nichicons, they're low ripple, you know, good quality, low ESR. So I got a good price on them. I think they came out to like 15 bucks a piece. So I got about $30 in those. I replaced those nasty looking old SCRs with some modern ones. These are 600 volt, 25 amp. So they're very stout and will handle whatever this amp can throw at it. I took the thin wires out and kind of ganged up some cables for your power and actually soldered them to the board. Anything that was in the power path with current, I removed those stupid little spade lug things. I don't like them. They come loose. You can kind of see that they were getting kind of dirty and tarnished, and that's what happens. So anyhow, we don't have to worry about that anymore. New capacitors. Just went over pretty much over the whole amp, tested everything, cleaned the fan, oiled it, disassembled it, took care of that. I replaced, if you look in here, I replaced these, you know, cheaper RCAs with a good set of gold contact RCA. You can see them down here. And instead of using just plain wire, I actually switched them out for shielded cable. So you can see the shielded cable. The wires for the speaker terminals are now soldered onto the board and no longer held on with those goofy terminals either. So everything else checked out really good in this amp. I'm really surprised how quiet it is now, and it really does put out that 205 watts. Actually, this thing starts to tap out somewhere around 215 watts per channel. So it's rated at 205 and into 8 ohms. I can tell you it very easily puts out and we're going to look at that here. And it can do that all the way from 20 hertz all the way up to 20 kilohertz, and I measured it at each point. I actually measured it at 20 hertz at 1 kilohertz and 20 kilohertz with both channels turned on full power, and it delivered. Now I'm going to turn this on and let you see, but don't pay attention a whole lot to the voltage reading on the scope, because this scope, the measurement isn't very good, and it's not my divider resistors. Those are accurate. It's actually the way this thing measures. You can see right now it's measuring 20 millivolts on this terminal. I don't even have anything turned on. I don't have anything connected, anything. So the measurements on this are not very good. Bottom line, I thought I would use that, but cheap scope, that's one of the things. The waveforms seem to be fine. When you measure the peaks, they seem to be correct. It's just the internal measurement is not great. And I think the reason is the resolution of that measurement is not that accurate. In other words, it's not going to, when it measures the RMS voltage, it's not going to measure it to, you know, 1/10 of a volt or 100th of a volt. It's you know, a little bit less of a resolution than that. So anyways, it kind of works. It gets you in a ballpark, but if you want accurate measurements, you still got to use the old true RMS meter, and that's the best way to get your measurement. So that being said, let's turn this thing on, and you can kind of see, did you see how the lights kind of flickered? And what it was doing was, you notice how they kind of pulsated, and that's because of how much current draw charging these caps up. That's actually the SCRs firing off with that soft start. They're kind of like their duty cycle. It's bringing up the capacitor slowly. So that circuit really works on this thing. So anyhow, I have seems like I can get full rated power out of this with about 1.52 millivolts RMS signal driven into the input terminal. So that's where we are right now. I'm sitting at 1 kilohertz and I have an 8 ohm dummy load. So let's turn on the channels and see what it does. And you can hear it. And of course the phone's gonna ring. Hold on. Okay, I'm back. Where was I? So turn these back on, and you can actually hear the thing whining in the background. You hear the 1 kilohertz tone, and you can see basically have full power going in there right now. Alright, and when I go up here and get things out of your way, you can see I have about 40.6 volts. Okay, and if we do our math on this, 40.6 times 40.6 divided by 8 is 206 watts. So you can see we have a nice clean 206 watts per channel, which is right where that thing's rated. And like I said, that's with 1.52 millivolts, or I'm sorry, volts RMS at the speaker terminals. Turn that back off. And the dummy load over here with that kind of power, I can feel it's warming up. But these are 300 watt loads, so I'm still have another 100 watts to go on those. So it, you know, it gets lukewarm when it's running. Now, a couple notes about this thing. If you guys decide to do this, I want to show you something. Hold on. Okay, hopefully you can read this. Make sure that I'm focused well. This is the part number, and this, I bought these from DigiKey, which is an American parts company. They're mail order, and these were only about $2.50 a piece, American. And the part number on these is an S6025 LTP, and what they are is, like I said, a 600 volt 25 amp SCR in a TO220 case. But the more important thing is, you see that ISO? These are actually isolated tab. What that means is that on a standard SCR, one of the elements, like the anode or the cathode, would be connected to the actual heatsink tab itself. On this, you do not want that. Make sure, if you order an SCR for this to replace and upgrade the SCRs, make sure they are isolated tab. If not, you can have a potential of up to 140 volts the peak between two of these, okay, and 70 volts between the other combination of the two. So that's very dangerous. If these come in contact with something, they would dead short to the chassis. But as long as we have the isolated tab, then there is no danger of that happening. The elements of the SCRs are not connected in any way electrically to these heatsink tabs. I also put a couple of different heat sinks. I mean, again, this was kind of hokey with this little rivet thing on here, and the heatsink compound is so dry that it's almost like paint now. So they weren't really doing their job very well. This looks a lot neater. They don't even get lukewarm. I mean, they're above room temperature, but just barely. The only problem that I may or may not address before I've really totally finished this amp up is this resistor right here, this 680 ohm 10 watt. That's the resistor I showed you on the schematic earlier that's in line with the fan to make it turn slowly. And when the amp heats up, again, you have these little pieces of nichrome wire that are connected to this screw here. There's just a little, if you look around, there's a nichrome wire right here. And when that heats up, that actually triggers this little, this little op-amp comparator circuit with these chips. And that's what can cause the little SCR to fire and short out this resistor and put full power to the fan and make it run full speed. This gets extremely hot. I mean, like, it will burn your hand off if you touch it. Now, I believe that if we put the case together, the airflow, even with the slow moving fan, will keep this a little more at bay. So I may just leave it as it is. As many years as this thing's been around, the solder joints didn't even get cracked or anything from the heat, so I don't think it's going to be an issue. I do have some metal chassis mount resistors for that I could make up, but kind of tight in here, it'd be hard to find a place to mount it. But other than that, that's pretty much everything. I really didn't have to touch any of the adjustments in here. There is a bias adjustment underneath on the board down here, but it was perfect. Everything was right in line. The amp is very quiet, and we can do a couple more tests. Let's now see what this does with bass, because of course it's easy to get your rated power at 1 kilohertz because every amp is always rated for that, so they kind of always design it to do its best there. But let's go to 20 hertz and see what we get, okay? And let's see if we can focus this even better. There we go. How's that? Just get everything nice. Okay. So I'm going to go to frequency 20 hertz. I want both channels. I want to align the phase. And this has to get slowed way down. Let's see what we got here. Okay, and you can see even at 20 hertz, 19.569 hertz, you can see 20 hertz. You can see just rock solid. And again, I'm getting 39.9, so I'm right at 200 watts. Okay, so it really only is dropping off a tiny bit of the power curve with the same signal driving in, just so it's a flat responding amplifier. And then if I go up to 20 kilohertz, all right, so let me set that, and let's get this to sweep much faster, and we got to go way more. And you can see at 20 kilohertz, and this is not reading properly. I'm at 20 kilohertz, believe it. Like I said, the measurements on this thing are not perfect, but at 20 kilohertz, rock solid all day long. Power is 39.42 volts RMS, which is going to be just a little under the 200 watts. So it's staying right around, it's peaking out at the 1 kilohertz at about 206 watts, and then at the extreme ends of 20 hertz and 20 kilohertz, it's tapering off maybe 5 watts from that. So it's a really flat amplifier all the way across the board. And now I did not hook it up to my distortion meter. I could measure the distortion on this, but you know, you could see the sine wave. It's very, very clean looking. You know, to me, it's kind of immaterial at full 200 watts per channel if I'm getting 0.2 or 0.5% distortion or 0.1. There, you can hear a little bit if you really have good, well-trained ears, but first of all, I never run my amps at full power. If I want that volume level, I get an amp that's, you know, double what I'm going to use. So I'm sure when you drop that power to 100, 150 watts per channel, it's negligible distortion. So, but even at the 200, it's listenable. So, you know, again, this is a tiny little amplifier. Physically, as far as physical size is concerned, and when you think about it, you're getting that much power out of this small of a package. You know, you know, some of the other amps I've worked on, like Adcom and Onkyo and some of these other bigger power amps out there, the Pioneer specs, they're double the size of this thing. And really, when you look at their output, they're really not doing anything more than this thing is. And they have humongous capacitors and huge diodes for the power supplies and massive output transistors. But it kind of gives you the idea of how efficient these MOSFETs are. They really are. And I could drop this to 4 ohms and it still will be just as clean, and it'll have even more output power because of the, you know, the Ohm's law and all that. It can deliver that current. So I hope you enjoyed this. Again, this was a Soundcraftsmen model PM860. Alright, so there's your front cabinet. And I don't know at what point my clipping light will go on, but we should probably check that real quick too. So before we wrap this up, let's look at that. Because you remember, this has those little true clip lamps. Okay, so I had about 1.52 volts RMS going into the inputs. I now turned that up to 1.60 volts. And you can see when both channels are on, the clip lights just start to light up. And that's at 42.28 volts. Okay, so let's measure that. And that's at 223.4 watts. So just around 220 watts at 1 kilohertz is where the clip lights will actually kick in and show you that it's clipping. And you can see the lights come on when you turn it on. And the funny thing is, if I just drive one channel at that power level, you can see that they don't turn on. But if I turn on both channels, even now they're just kind of clicking on and off. But because of that, that's telling me that the power supply is what's dropping out. It's not the amplifier itself. And again, a soft power supply is, you know, it's all about the transformer and the capacitors. And unfortunately, you know, that, you know, the Pioneer SX1050 is only 120 watts per channel, and we're using 20,000 microfarad. Here's one right there. 22,000 microfarad capacitors for a 120 watt amp. And this is a 205 watt with a 15,000. So it's basically draining the caps a little bit too fast when you get above. So my gut feeling is, if you put a heftier power supply in this amp, the amplifier circuit is so solid in this, it probably could handle you know, closer to 230 watt per channel. Not that that matters a whole lot, you know. When you talk a perceived volume, you know, to your ears, there's really not a whole lot of difference between 205 and 225 watts of power. You know, that's kind of a misnomer. Watts, doubling the watts doesn't double what your ear hears. It just doesn't work that way. But anyhow, we can get into that in another video. I hope you like this. I actually have another thing to go right up on the bench right after this. I actually have a couple things I have to fix for work. And then I have another thing that will go very well with this amplifier, and should be an interesting video as well. So, hope you enjoyed it. Give me a thumbs up. And as always, it's been fun doing this, and hope you enjoyed it as much as I did. Have a great day.